design and analysis of algorithms. If you are listening to this particular lecture, proof of master theorem, congratulations, because you have decided to be not average. Most of the average engineers in computer science skip this kind of chapters. It's an advanced concept and it will help you become better in your field by a huge margin. So without further ado, let's try and understand what is the proof of master theorem. But before that, let's understand why do we want to what are these variables A and B, which I talked about a lot in the last lecture. Why do we want them? What are they? And how do they look like? So here's an example over here. I have a simple array which has numbers from 1 to 6, right? So the length of the array, n, is equal to 6 in this case. Suppose I'm dividing the array into half in each recursive step. So 1, 2, 3, 4, 5, 6. I partition the array at the half. This side, so we can see that the array length has dropped by 2. What I mean to say is that n was 6 in the first step. In the second step, n is equal to 3. So you can say that b is equal to 2 because the partition of the array made into half and half. Now how many such arrays were created? 1 and 2, and that is your A. So you divide the array into two halves, that is A, and how do you divide them is B, right? And it does not clear right now. It will become more clear as we go to the proof and as we see questions regarding master theorem in the future. But this is the general concept, like how do you divide and where do you divide? That stands for A and B. Now this was a very simple example, but usually in computer science you will have cases like these, where fn is the function at the beginning. You divide the array into each halves. You divide the array by b, and so again, number of times you divide it is a, and how do you divide the array is b, or the number of outputs after dividing the array is a, and where do you divide them is again b. Now it will, using our own common sense, we know that every single step it will branch out even more. For example, here in the first case, if n is 6, second case we just have two new arrays, right? Suppose here is 3 or something else. But if we go further, we know that it would be like suppose 3 over here, for example. So in every single step, or as you go to the bottom of the tree, the number of leaves increase, right? And in a tree, in this particular tree, master theorem helps us to know that these steps, this division is predominant, or the calculations at each of these steps is predominant. That's all it compares. So for the proof of master theorem, first of all, we have to calculate ourselves what is the width of the tree and what is the depth of the tree. So this particular lecture is a bit math intensive. I would request you all to brush up on your skills in logarithms, because we will use a lot of logarithms in this particular lecture. So let's start with calculating the depth of the tree and the width of the tree, and then move on further into the proof. Step 1, step 2, up to step some x, where you have theta 1 computation. So basically it means that at the beginning you have the entire array, it gets partitioned into 2 or 3, and further down, and finally you have a single part of the array where you have to do the final computation. Now, in this particular one, we want to do something is that calculate the depth of the tree and calculate the width of the tree. And these are a good problem. So let's suppose that there is some x, b to the power x, for which this is 1 in this step. At this step, n by b, this has to be 1 for some particular x. So using logarithm, it's x is equal to log n b. simple transformation, and if you're having some issues, I'll recommend go on Google and just like brush up your skills in logarithms. So the depth of the tree is log of n by b. Now we have to find the width of the tree, right? So for calculating the width of the tree, so at each step, if you can carefully observe, the first one, there are a number of leaves, right? A number of leaves at the height of the tree 1. At the height of tree 2, there is a squared number of leaves. So at the height of x, at height x, there are a to the power x number of leaves. So a power x is the width of the tree, or the number of leaves of the tree, a power log nb, right? And we'll use some basic skills of logarithm to make it, to change it in a way which is have b log. Let me see, what can I do with this one? Let's try this one. So a is actually, it's like a logarithmic thing. You can write a as b power log a by b. So I'm substituting the value of a from this equation onto this one. So it becomes b log a by b into log of n by b. So what I do is b log n by b. I'm just like swapping these two because it's multiplicative. I can do this thing, log a by b. So this one becomes n using the same equation. If you can substitute n over here and bb, this becomes n. This becomes b power log a by b. So the width of the tree is n log a b. So this is the depth of the tree. This is the width of the tree. And if you can carefully observe the pattern, this is where we talk about Master's theorem. We take the n log ab and compare that with the function fn. So this is where it comes from actually. So in the previous whiteboard slide, we calculated the depth of the width of the tree or number of leaves, which was n log ab. So if you want to calculate number of leaves at each step, this is the method, right? The first step it's fn, just one leaf. Second step it's a into fn by b. Third step it's a squared and b squared, and coming down it's n log ab. Again, if you have doubts on how this ab came, n log ab came, go to the previous whiteboard slide. So now our task is to calculate the summation of number of such leaves, and for that gives us our Tn, the function which we are trying to compute against. So Tn is equal to summation of a power j fn by b power j. So this j is like, you can take from here like number of steps at each subsequent depth, and the summation will go from 0 at this step where a and b is 0, a power 0 is 1, b power 0 is 1, from here to a step before this, because we know the exact number of leaves at this particular step when b power j is equal to n. I'm talking about the step where b power j minus 1. So we compute from j is equal to 0 to j is equal to log n minus 1 b, a step before. So we reach here, and at the end, because we know that this is the one we have to calculate, we just add this to it. So this equation is from here to here, this part, and for this and this last part from here, and this last part comes from adding up the number of leaves of the tree. So from here on, from the next slides, the next whiteboard slide, I'll take off these diagrams and I'll just go into the proof and show you how do we come to case 1, case 2, and case 3. I will also attach with this particular lecture a PDF typed in LaTeX, where if you have any confusions with the proof, you can go through it, because the proof requires good amount of knowledge from logarithms and also from APGP, like arithmetic and geometric progressions. Here we'll deal with the first case of the master theorem, where fn, the function, is equal to on n log ab minus some epsilon. So what it basically means is that this particular function, the tn side of it, is dominant, and we'll prove that if that is dominant, then we will just care about n log ab. I mean, so in this, so what this case means is that if this side is dominant, we only care about n log ab for deciding the time complexity of this recursive function. So let's start with the proof. We saw in the previous slide, whiteboard slide, that to calculate gn, we have to have the summation of this and then plus the constant term for the last one, which is again like n log ab, which will come later. But this is the basic of solve first thing. So substituting the value of fn over here with this one as per the equation, as per the case. So it's summation of something a j f, then n by bj log of a b minus epsilon. So again, I'm clarifying again, we are substituting the entire value, hence like this entire thing comes as a power of this function, right? Or the function goes away, sorry. And then we can take the constant term n off from this, because the summation depends upon j and not a, b, or epsilon. So we can take this entire constant thing, n, a, b, e, outside. Then summation of a of j 1 by bj log of a by b minus some epsilon, which means, let me just focus on this part first, we'll come to this part later, which means that summation of a j, and then we can group them up, bj log ab into bj into some epsilon. So I'm just like reversing this particular one because it's a minus. I can reverse that, right? So bj epsilon. And then next step I can do is summation again, a of j, wait, let's just take common. So a b log of a by b, this one comes here, into b epsilon and whole power j. Now this step makes sense because I'm just swapping the powers, and after this I can write them as, again, so these are like few tricks from logarithms. Summation of a dot b e, this one becomes a, because we know that this one holds true, this equation. So using this particular formula, we say this is a, this cancels out. So this is be whole power j. Summation j is equal to 0 to j is equal to log n b n minus 1. So this terms, so this means that we are adding something like this. So first is 1 plus be plus be squared up to be up to log n minus 1 b, log n minus 1 b. You have to sum this. This is simple geometric mean, which is in geometric series summation. So which is Rn minus 1 by 1 minus or R minus n. I mean, let me just write the formula real quick. R minus 1, which means R is b power e, n is log n minus 1 d, and then this side subtract by b e minus 1. From here to here. You might be wondering where this minus 1 went. I just took it off because it just makes the calculations easier, and it's not significant to our like series of for largely n. In the next step, so this one comes from this part we had brought outside the summation. This one comes from inside the summation, right? So it's n log a minus epsilon b, and this is, so again we can swap these two, log n b and epsilon. So by bringing this one closer, b power log n by b becomes n dot epsilon minus 1 b dot epsilon minus 1. This is computer science. We can ignore the constants here because we only care about the overall polynomial asymptotic notation. So ignoring these constants, it becomes n log a d minus e into n power e. So the e and e cancels out over here. Like when you multiply it, adds to it, it cancels out. So it becomes n log of a b. So this is the proof for the first case of master theorem. In the next whiteboard slide, we'll look at the second case and then the third case of master theorem. So the first one is the most complex one in terms of using, I mean, you have to have concept from arithmetics, from logarithms, so it requires some concept. So please brush up your skills in logarithms if you want to like solve this one. And this one is fairly straightforward, unlike the first one. So substituting it, it becomes log n minus 1 b j0 a j n b j log a by b. So again, we can take the n log a b term outside of summation because that is not dependent. All these are constant for j. So it's n log a b summation from j to some log n minus 1 by b. Inside it's a power j divided by b log a b into j. Just rewriting. And this one, this term becomes a. So again, a of j, just taking this one bottom here, this becomes a of j, this cancels out. So we have n log a b summation j to 0 log n minus 1 b 1. I mean, this simply means that add 1 1 1 1 from 0 to log n minus 1 b times. So this equation is nothing else but n log a b into summation of this one, which is nothing but log of n b. This is clear? So if you recall the second case of Master's theorem, the formula for that, or the time complexity for that, was n log a b ln It's proved. Welcome to the last case of Nashville theorem. This is the third case where this particular recursive function a f n b plus fn. So here we compare this one and we say that this part is dominating, fn is dominating, and hence the time complexity of the entire recursive function will become the time complexity of this fn. So to prove that, we have to have certain assumptions that a, f, and b is less than some constant c, fn, where c has to be less than 1. And this is important because we'll use this fact later on. So c has to be less than 1. And again, this is a straightforward case, no-brainer, where we just substitute the value of this particular part with this one and just solve it off. So substituting the value of a, f, and b with this one, less than, because it's a less than over here, summation of log n minus 1 b j is equal to 0. That becomes c, probably j fn plus some constant 1. I mean, this can be like 1,000, 10,000, anything, any constant over here. But ultimately, this particular expression is greater than equal to the above one because of the condition given to us. So we can pull out fn because it doesn't depend upon j or something. And then summation of j is equal to 0 to log n minus 1 b c of j, some constant, so 1. Again, here fn. So if we assume that this one extends to infinity, like there is no upper bound, right, and the value of c is less than 1, in that case, the geometric sum of that series is nothing but 1 by 1 minus a. Summation of a from 0 to infinity, or like from 1, I think. From 1 to infinity is 1 minus a, provided a is less than 1. So applying the same formula here, it becomes 1 by 1 minus c power j, and then some constant O1 over here. So from here we see that these are all constants, and we can, like, these are all constants, right? So we can say that fn overall, when these numbers don't have anything inside them which is polynomial. So fn is the one which, like, in terms of computer science, which strives after all these equations, and hence we can say that gn is equal to theta of fn. I mean, they can be some constant, but it doesn't matter. So with this particular slideshow, we end our proof of Nashville theorem. I hope you gain a lot of knowledge from this. Nobody in the world is perfect. I have taken huge resources for this lecture from the book from Corman. I can, like, share the link in this particular lecture. So I've taken huge resources from that particular book. Again, I've my own experience, and I've gone through several other, like, books or lectures, but mostly it's from the Corman book for algorithms. So I'll suggest you all to, after, like, seeing this video, go and read the Corman book, or you can just, like, read and see these explanations whenever required. But again, I'll say you guys that congratulations, putting the effort to study proof of master theorem speaks a lot about your own interest in computer science, and this will take you far. Most of us won't come to this lecture. They will just go to master theorem, look at the 3 cases, and learn how to solve them, and go in the exams or go in their interviews and just, like, say that. But coming here, understanding the proof of master theorem, going to the book Corman and further validating it, that will set you apart. That will make you above average. That's when you can start, you can apply and get jobs at Facebook, Google, or have your own entrepreneurship company, or go for PhDs, something in the life, something in the field of computer science. So if you have interest if you have genuine interest in computer science and if you see yourself excelling in this field, you have to take such initiatives where you go beyond the course requirement, beyond what most people understand, and beyond to a place where you have to brush up your skills in mathematics, in calculus, probably in arithmetics, all these things. So once again, it's a nice, beautiful day outside. I hope you guys have fun in learning this chapter. If not, go outside and have fun. Thank you so much, and see you in the next lecture soon.